This is transmission line analyzer, model number TLA05. Switch on the instrument from the back panel. Now this is the impedance bridge. It goes from 0 ohm to 1 kilo ohm or roughly 800 ohms. This is an unbalanced load. This is a frequency output source which goes from 30 megahertz to around 300 megahertz with the help of this tune pot. Now it is showing around 7 megahertz as the lowest frequency, and here it is showing around 300 megahertz as maximum frequency, whose sweep or bandwidth can be controlled with the help of a span pot. Now there are two outputs, horizontal and vertical, which can be used to display the frequency sweep of this frequency source. Then there is one more portion of transmission line analyzer, that is TDR, time domain reflectometer. It has got short range and long range. Short range gives a pulse output of around 10 megahertz with a 1 volt peak to peak level roughly, and similarly this gives a typical 100 kilohertz of pulse waveform with 1 volt peak to peak output. Now let us start with the frequency response of cables by connecting horizontal and vertical output to any oscilloscope available in your lab. For example, we are using a DSO here. One can use an analog oscilloscope as well. Now put the oscilloscope in XY mode. Some oscilloscopes have got a direct XY switch. Press that switch. Now there is a spot coming on the display which indicates that the display is now in XY mode and the no time base is used now. Use XY cables. These are XY cables. These are ordinary cables because they don't have a very good frequency response, so they are used for DC. The horizontal output is actually a triangle waveform. Now X output is connected to channel 1. Now see, the moment X output is connected to channel 1, we see a line. Then there is another XY cable which is connected to vertical output. Vertical output is nothing but DC output of the frequency which is displayed here. There is basically a detector inside it which converts the RF frequency into DC voltage. Now this output vertical is connected to the Y channel or channel 2. Now what you see is a frequency response. If your display doesn't come, then you have to select the attenuators of voltage at X or Y. Now here it is less, you have to select it accordingly so that the display almost comes in the center. Now to ensure that we are measuring the center frequency, because whatever is displayed here is actually the center frequency. If I remove the Y cable, I can see now this has to be precisely put to the center. Now this is actually 136 megahertz which is being displayed here. Now we put it to 150 megahertz. Now the frequency here is actually the center frequency. Now the center frequency is this. So when we are keeping the display at 150 megahertz center frequency, that means this is supposedly the low frequency and this is the highest frequency, that is roughly around 300 megahertz. And the coupling has to be DC so that the waveform doesn't go left or right. Okay, now what you are seeing is actually the frequency response and this is a calibrated attenuator. So suppose if I press 0.5 dB, I could see 0.5 dB on oscilloscope is roughly this much. If I press 1 dB, I could see 1 dB is this much, 2 dB is this much, 4 dB is this much, 8 dB and 15 dB, almost 0, which again can be amplified with the help of voltage variable attenuator. Okay, now let us take a cable. This is RG58 cable, 4.6 meter length, and the characteristic impedance of this cable is 50 ohms. Now the moment I try to feed energy with the help of this frequency source into this cable with other end being open, what I see is number of multiple standing waves. Now here the span is kept fully clockwise so that you are seeing the complete frequency response. Now if I turn the span anti-clockwise, I can see a particular standing wave at 150 megahertz. Now if had the span been almost 0, then I could have only see a maxima, but here the span is kept little, say like 10 megahertz or 15 megahertz, so that one can always see a standing wave being formed. Now as this end is open, so the VSWR is maximum, and if this end gets shorted, you can see the VSWR again is maximum. So now you can see the moment I connect this cable, now it is open circuited, and the moment I connect it on a short, the maxima changes to minima. And when I sweep it completely, I am unable to see the difference between maxima and minima because it's very small. Though it is, as you can see here also, if you see the center, earlier it was minima and now it is maxima in open circuit. And suppose, now because the load is either short or open, that is why we are getting maximum number of reflection from the output end and number of standing waves are being formed. Now if the load is equal to the characteristic impedance of cable, that is the termination is equal to the characteristic impedance, then no energy would be reflected back from the load end. And now I am trying to make the load impedance equal to the characteristic impedance of cable, and as you can see, this being lower frequency and this being higher frequency, I can see the standing waves are almost null. So very less standing waves or almost negligible standing waves are being formed up till 200 megahertz. But as we increase the frequency, we are not being able to null the standing waves because the load being purely resistive. But at higher frequency, the cable needs a reactive or inductive component because the characteristic impedance gets R plus jx. So it has to be cancelled, and which a purely resistive load will enable to cancel the standing waves. Now as you can see, the impedance is roughly around 50 ohms with RG58 cable. Now suppose I connect another cable. This is now a RG59 cable. This is a 75 ohm cable. Now the output impedance of source is fixed at 50 ohm. So we will be having a little mismatch while feeding this cable. Now here you can see the standing waves being formed. And now I try to terminate this cable on a 50 ohm load, and you see the standing waves are very much visible as compared to a RG58 cable. So we are for sure that the impedance is not at least 50 ohm. Then what is it? We try to null the cable at around 75 ohm, and we see that at 75 ohm a little improvement is there at low frequency, but at higher frequency still the standing waves are not being cancelled. This is because the output impedance of source is 50 ohm and we are feeding a 75 ohm cable. So we can always discriminate that this cable is not 50 ohms. So it is roughly around 75 ohm. Similarly, now we connect a lossy cable. This is a lossy cable. Now the moment I connect a lossy cable, now you can see the VSWR has decreased because the energy is not being able to reflect back because of the loss of the cable. So instead, as we had seen earlier in 58, this VSWR was very good even at high frequency, but at high frequency the losses being more, the VSWR is less. So now you can see the attenuation here. Now if I terminate this cable, now you can see it is getting terminated at around 40-45 ohm, but but the standing waves are still there, though they have been nulled to an extent. So you can say the impedance is around 45 ohm for this cable. Similarly, we have got one small cable, again a 50 ohm cable, that is RG174 cable. Now here you can see it is little lossy as compared to RG58 because the VSWR is less. It should be maximum. Now you can see it is getting nulled at around, again similarly 50 ohm. It's very small difference, but still we can predict that it is roughly around 50 ohms. But nulling is not as good as it was in case of RG58 cable. Now we have got a 300 ohm cable. This is a parallel wire transmission line. Now as you can see, we have to open this cable because there is no shielding. So the current is flowing in both of these conductors, and one part is picking the other part, so it has to be opened, otherwise you cannot check this cable. Unlike coaxial cables, which has got a braiding outside the dielectric, so even if there is shielding, they can be tested like this, but these cables can never be tested like this. They have to be opened. Now there is a balloon which transforms the impedance from 75 to 300 ohms. Now you can see that I have opened this cable, and the moment the way I am touching the cable or I am straightening the cable, the standing waves are changing at high frequency. Now this cable has already been terminated. Now this is an unbalanced load, so because the outer is ground and center the current is there, but the current is flowing in both of these conductors. So we need a balanced load, and that's why we have put a balanced load in the cable itself. Now putting the switch in 300 ohms, you can see the standing waves are a little less at low frequency, and now I switch it to open, and you can see the number of standing waves are being formed. As you can see at the center, it's roughly showing a maximum, and it is short actually, and this is a three-way switch, and now it is open. Now you can see the standing wave. Now the maxima has been changed to a minima here, and this is the termination. Now the termination is not very good because at low frequency this cable has got good response, but at high frequency the characteristic impedance of cable is not 300 ohms.